So today we are going to finish our treatment of the atom. We're going to complete our analysis where we've developed our full formal theory and finally applied it to the basic unit of nature that we began with, the existence of the atom. But now we have full understanding of this system within our formal theory and a particular goal we have in mind. It's always good to have the goal in mind for the lecture, is to understand precisely then why we get the energies that we get, which in the natural units in which we've been working turn out to be minus 1/2 1 over n squared, where n is a natural number. If we can explain where this formula comes from, we then have our complete understanding. Where we were last time is we had derived the effective one-dimensional Schrödinger equation, which describes these allowed energies and the corresponding wave functions. It has the typical form of a Schrödinger equation, or kinetic energy operator, in natural units minus 1/2 the second derivative of our function. It then is multiplied by some effective potential, which we will look at in a moment, and that then returns back these allowed energies times our wave function back again. We should recall that we are working in spherical coordinates, so the valid values of r actually are only those that are greater than or equal to 0. We then went ahead and we sketched the basic behaviors we would expect from a system like this. So I'm showing you here a plot of the potential versus the radius for this particular effective potential that I'm showing to you here. And we noted that as r goes to 0, we have this very strong repulsive centrifugal potential pushing us away from the origin. Then at large distances, we are dominated by this decaying Coulomb interaction, which goes like minus 1 over r. And as we go out towards infinity, this actually becomes something that will approach the constant 0. Now, we further went on to look at what would happen for a bound state energy, at which point, of course, we would expect that that bound state energy has to be less than the potential at infinity, so it will be some negative value for the energy. And then we began to consider the behavior of the wave function and the resulting 3 different regions, where we have a classically forbidden region near the origin, an allowed region in the middle, and a classically forbidden region again off to the right. Now, to represent the fact, if we really were solving this as a one-dimensional system, that r can never be less than 0, you can think of it this way if you like. We can hash out the region r less than 0. And if you like, at least intuitively, it's not 100% rigorous, but it brings you to the correct conclusions, you can regard the effective potential for values r less than 0 to be infinite. Now, if we then focus on the behavior on these extremes, as r heads towards infinity or r heads towards 0, we came to some very important conclusions. First, as the radius goes out toward infinity, because the effective potential approaches 0, it therefore is becoming a constant, and you guys are experts now at dealing with bound states in piecewise constant potentials. You know that the wave function in this region, when the potential becomes a constant, must be a combination of a growing and a shrinking exponential in general, so that we are curving appropriately away from the axis. You further know that if this is our final region, to maintain normalizability, we cannot have any amount of this growing solution to maintain normalizability of our wave function, and so therefore we can reject this term, and we know we're seeking only a decaying exponential term. Finally, you also know quite a lot about the decay parameter alpha. We've written this down many times in traditional units. It's always root of 2m over h bar squared, the value of the potential, in this case our effective potential, minus the energy E. We are working in natural units, so h bar squared on m has the numerical value 1. Also, we are talking about a region where the potential is vanishingly small, so we can replace the potential with 0, and immediately we see then that alpha is square root of minus 2 times e. Now, you guys know how to also work with a decay parameter alpha. As you've seen in the past, we generally derive some kind of an equation. Typically, it's a transcendental equation for alpha that maybe you have to solve graphically. And then you read off the values of alpha from the graph, and finally, to determine your bound state energies, you solve this equation, which would then give us alpha squared times a factor of 1 over minus 2, and this then would be our formula for the energy expressed in terms of this alpha. Today we will be following a very similar strategy. We are going to solve for alpha. And notice, as soon as we know what alpha is, what we're hoping to find, the translation of our goal into this traditional way of looking at things for us is that if we can prove that there's some equation out there that insists that alpha must be 1 over a natural number, 1, 2, 3, etc., inserting that value for alpha, we will then have proved our key goal and have understood the atom. To lead us toward that understanding, we had also, of course, to consider the other region, and we carried out an asymptotic analysis of what happens in this region where the potential is going towards infinity like 1 over r squared. We there again found that there were two linearly independent solutions, so that our general solution is a combination of those two. And we found that monomials were actually the form of the solution we would expect, and there were two different powers in those monomials, either L plus 1 or r to the minus L. So once again, we have a general solution that would look like so, which must always be curving away from the axis. And you can see that indeed the two forms that I've sketched do exactly that. We further argued, though, that this r to the minus L term, particularly if L is 1 or 2 or 3, is going to diverge towards infinity as r heads to 0, and this will prove actually also to be not normalizable. So we can simply reject this second one as any possible form and thereby impose the appropriate boundary condition. You will notice that because L is always at least 0, by sticking to the first term, we are ensuring that we have at least something that goes like r to the 1, right? So at least we know it goes to 0, which comports with this kind of intuitive way of looking at it, that we have some infinite potential here for r less than 0. We, however, gave a rigorous proof of this behavior by looking at the normalizability. The one tiny exception to that is this issue about what happens when L equals 0. There is a special case that requires special handling, and I want to just lay that out there as a challenge to the listener to try to figure out what actually rules out this solution in the case when L is 0, and then we would be approaching the origin not as something that would vanish, but something that would be a constant. Finally, our main plan of attack then is that having seen what these asymptotic behaviors are, the plan is to then express my wave function as a product of these two terms that capture the appropriate asymptotic behavior, times then some other arbitrary function which I'm going to call P of r. Remember, rho has the curly tail, P has the straight tail. When I do this, I'm not losing any generality. I'm not forcing this form on my wave function because, after all, rho of r is just defined to be whatever the real wave function is divided by these two factors. But by doing this, I encapsulate most of the important behaviors already into these factors, and so then the hope is that p will be some relatively simple function, something that I can analyze then in some kind of very convenient power series. So the mathematical approach we could take then would be to insert this series expansion in for this third factor and then insert all of this into my differential equation. The result of that, though, is going to be a very complicated mess, if you think about it, particularly since I need to take two derivatives of a product of three factors, one of which is an infinite series. So we are going to first develop a strategy to minimize the algebraic complexity and thereby keep our chances for errors as low as possible.